Welcome to part 5 of the module that provides a case study of gang of 4 patterns. In previous parts in this module, we first described the object-oriented expression tree case study. We then evaluated the limitations with the algorithmic decomposition of the expression tree. We presented an object-oriented design of the expression tree processing app, and we summarized all the patterns in the expression tree application, focusing primarily on the gang of 4 patterns. In the remainder of this module, we're now going to be presenting each of these patterns in turn, starting with a set of patterns for tree structure and access. Here's the overview of the tree structure and access patterns. The purpose of these patterns is to define the key internal data structure for the expression tree, and then be able to simplify access to this data structure, reducing the complexity of memory management and using it in value-based contexts such as STL containers. We're going to talk about a pair of patterns in this part. First, we're going to talk about the composite pattern, and then we're going to talk about the bridge pattern. So first, let's discuss the motivation for the composite pattern. The goal of this part is to support the physical structure of an expression tree. In other words, the binary and unary operators and operands. We're also going to be able to provide hook methods that will enable arbitrary operations on the nodes in the tree. For example, we might want to be able to print every element in a tree. We might want to go through the tree and apply an operation to evaluate the tree to get its yield or its value. Some of the constraints here, we want to be able to treat operators and operands in a uniform way. We don't want to have to make distinctions between one and many to avoid special cases. And another thing we're going to do is we're going to eliminate the need for any kind of switch statements and type tags, which is something that we were not able to do with our algorithmic decomposition. And I'd mentioned at the time in previous part how that made it more difficult to evolve the expression tree processing application without having to do major surgery to the code, which is tedious and error-prone. The solution we're going to apply here is one based on recursive structure. We're going to model an expression tree as a recursive collection of nodes. These nodes will be represented as a hierarchy that captures the properties of each of the different types of nodes. For example, the leaf nodes will contain no children. The unary nodes will recursively contain one other child node, and the binary nodes will recursively contain 2 other children nodes. Here's an interface that we're going to define called component node, and this is the abstract base class for composing together the various expression tree node objects. As you can see when you look at this interface, it's got a virtual destructor, which is a C++ feature that ensures that the subclasses of component node will properly be deleted when we delete an object through a pointer to the component node class. And it also defines a set of operations to access various parts of the node, its value, its left child, its right child, and so on. And it also has another very important method called accept, which is a hook method that'll play an essential role later when we talk about the iterator and visitor patterns. The subclasses of component node will include things like leaf node, composite unary node, composite binary node, composite add node, composite subtract node, and so on and so forth. These form the various parts of the composite of the tree. If we step back and analyze this from the point of view of commonality and variability, you can see that this base class interface is used by all the nodes in the expression tree, and the variability, which is also handled in a common way, is to allow each subclass to define whatever state and method implementations are specific for that type of node. Here's an example that illustrates the hierarchy of these nodes. As you can see, this is a much richer data structure than our very simple tree node struct that we had used in the algorithmic decomposition example. Note in particular the inherent recursion in this hierarchy. So a leaf node is a component node. It inherits from component node. Moreover, composite unary node is a component node. It inherits from it, and it also has a component node. It has a pointer to an instance of something that's a component node, which is its child. Likewise, the composite binary node is a composite unary node. In other words, it inherits the properties of the composite unary node class, and then it goes ahead and it has a pointer to a component node. So these recursive properties of the expression tree are revealed and are institutionalized and reified in our class hierarchy for the component nodes. One of the benefits of doing this is it eliminates the need to have type tags and switch statements because we're treating all the different kinds of nodes in a uniform manner. Well, it turns out this particular way of arranging the structure of the tree forms a pattern from the Gang of Four book called the composite pattern, which is an object behavioral pattern. The intent of this pattern is to treat individual objects and multiple recursively composed objects in a uniform manner. You might decide to apply this pattern under certain circumstances. For example, objects need to be composed recursively, as is the case with our expression tree. We don't want to distinguish between individual and composed elements, and we want to be able to treat the objects in the structure in a uniform way. This slide also illustrates the Gang of Four UML diagram that illustrates the relationship between these various roles and responsibilities. We have the component class, which is the base class, such as our component node. The pattern defines a composite class, which, as you can see, inherits from the component class and also has one or more pointers back to components. That's the recursive nature. In our example, this would be things like component unary node, component binary node, composite unary node, composite binary node, composite add node, and so on. And then we also have a leaf node, which inherits from component node, and which is used to provide the leaf elements in our particular example. These would be the numbers or the operands in an expression tree. Here's an example of how we could use this pattern to implement a particular expression. If you take a look here, we're going to have our example where we've got -5 being multiplied with 3 plus 4. So we can use the composite pattern to build the expression tree based on these recursively composed objects. We'll start out by defining a number of component nodes that actually point to leaf nodes. So we have leaf node for 5, the operand 5, a leaf node for the operand 3, and a leaf node for the operand 4. And then we go ahead and we build 2 more types of component nodes. In this case, we're going to have a composite negate node, which is going to negate 5, and we're going to have a composite add node, which adds together the leaf nodes for 3 and 4. And then finally, we end up with another component node, which in this case is a composite multiply node, which is going to contain the -5 subtree and the +3, 4 subtree. In C++, we're going to have to consider the implications of memory management. How are we going to go ahead and free up this data structure later when it goes out of scope? If we take a look at a Java implementation of the same pattern for the same expression, you can see that the code is very, very similar. You allocate a bunch of leaf nodes and various types of composite nodes. The main difference between Java and C++ is we don't have to be as concerned with memory management. The Java garbage collector will free up this memory when it's done, thereby alleviating the application developer from having to be responsible for deleting it explicitly. There's a number of consequences of applying composite. Some of the positive benefits are much greater uniformity. We treat components the same regardless of their complexity, in other words, their nesting depth, or their behavior. They all have the same interface. Likewise, the solution is very extensible. New component subclasses can work wherever the existing ones do, so we can extend without having to break what we've already got, which is very different from our algorithmic decomposition, where we had to go in and perform surgery on the tree node structure to add new type tags, make changes in our algorithms to add new cases for our switch statements that switch on those type tags and so forth. The solution here is also more parsimonious. The classes, the subclasses, only need to provide the fields that they actually use. So for example, a component node really has no state at all. A leaf node only contains the integer value. The composite unary node only has a left subchild for its one child. Likewise, the binary nodes have 2 subchildren. But the leaf child doesn't pay the cost for the composite nodes. And that, again, is different from our algorithmic decomposition, where everything was glommed together into one big struct and union that always had to make worst-case assumptions. There are some potential downsides to this pattern, one of which is the perceived complexity. When you use composite, you end up with a lot of subclasses, a proliferation of subclasses. And that may appear at first glance to people who don't understand the pattern as though it's prohibitively expensive in terms of the surface area of the solution. You can also end up with somewhat awkward designs as well. You may need to treat the leaves as lobotomized composites in some case. For example, in our example, we have the situation where a leaf node has methods for left and right subchildren, even though a leaf has no left and right subchild. So we're going to have to think through how we deal with that and how we keep people from making mistakes because of that commonality. There's a number of implementation considerations to think about when you go ahead and apply the composite pattern to your code. Do the components know who their parents are? If so, they probably need some kind of back pointer or some up pointer to go up the tree, which we'd have to go ahead and add. Do you really want a uniform interface for both the leaf nodes and the composites? In our case, for simplicity, we have a uniform interface. But as I mentioned before, that means that leaf nodes have operations that don't really make sense in the way that they're going to be used. We want to make sure we don't allocate storage unnecessarily for the children in the component class. We don't want to have situations where component adds a lot of state because all the subclasses are going to end up having to incur the cost of the state that they have. This is one of the major problems we had with our algorithmic design. Another issue to consider is who is responsible for deleting the children. Do they delete themselves? Are they deleted when they're enclosing? The subchild is deleted, the tree that encloses them, and so on and so forth. And there are different implementation considerations you need to think through. And the pattern will help give you guidance for different alternatives. There's a wide variety of known uses for the composite pattern. Many user interface frameworks tend to use it to hold various structures. Drawing editors tend to use it to deal with different kinds of glyphs. If you take a look at things like directory structures in Unix or Windows, they are done in a recursive way. And you can imagine writing programs that traverse these things and take advantage of system calls that mirror the inherent recursion in these composite structures. Naming contexts in Corba are implemented as composites. You have a naming context which can contain other naming contexts or particular object references. And finally, internal representations of various kinds of structured data, things like MIME types or XML documents, can also use composite internally if you build the expression tree up concretely. So that wraps up the discussion about the composite pattern. The next thing we're going to do is we're going to segue into solving another problem related to composite. This problem deals with encapsulating variability and simplifying memory management. The goal here is to be able to encapsulate sources of variability in our expression tree construction and use. For example, if you look at the slide here, you'll see that we have a composite add node that matches the picture of the tree, and we're going to be able to encapsulate that and all of its dynamic allocation and so on inside of a special object called an expression tree object. We're going to be able to do this to hide the recursive internal structure behind a simpler interface. One of the other reasons we're going to do this is we're going to be able to allow ourselves to use various STL, so C++ standard template library, idioms, and patterns, where we're going to be able to iterate through all the elements in the expression tree without revealing the internal structure. We don't care how it's structured internally. We don't care how it's designed internally or what kind of expression it has and so on. And we want to be able to shield that from the end users. Notice, by the way, in this particular example that we're leveraging one of the new C++ 11 features called the auto keyword, which can be used to automatically deduce the type of the iterator based on the return value from the factory method begin. We also want to be able to simplify memory management. This, again, is more important in C++ than in Java because C++ requires you to manage the memory more explicitly because it doesn't have automated garbage collection. One of the things you have to take very great care of is if you write code like this where you allocate a lot of memory, you have to be careful when you go to free it up. For example, if you're not careful and there's an exception or a return statement or something else that prevents this delete statement from being called, we can end up leaking memory. And that's a very problematic issue with C++ that we'd like to clean up. Another constraint to our solution here is we want to account for the fact that the C++ standard template library has algorithms and iterators with so-called value semantics. In other words, they call copy constructors when you pass things from functions and return values from functions. Here's an example from a pre-order expression tree iterator impl, which we'll talk about later. And this is used for traversing an expression tree in so-called pre-order. As you can see, the way you do this is typically have a stack. And we're going to use a stack of expression tree objects. And when you go ahead and push the particular expression tree onto the stack, we want to make sure that we are very conserving in the overhead of doing deep copies. In fact, we're going to rely on reference counting in order to make this operation much faster, and easier to work with. But we have to make sure that we maintain the value semantics of STL that's expected by the algorithms and containers in STL. So the solution here is multifold. First, we're going to create an interface class, the expression tree, that will be used by client applications, such as the loops using STL algorithms and iterators. We're then going to create our implementer hierarchy based on the composite pattern with things like the component node and its various subtrees. And when we combine these two things together, this helps us to encapsulate the variability more effectively. The interface class, the expression tree, can use C++11 features or boost features such as shared pointers in order to be able to do reference counting so that you don't end up making deep copies when you pass these particular objects by value, which is a nice simplification, and it reduces the amount of memory and overhead in terms of time and space in the program. We're also going to see later how we can use the abstract factory pattern to create the appropriate type of composite hierarchy that is then glued together with the interface that we're using here with the expression tree. Now, here's a view of the expression tree class interface. This is the interface for this composite structure that contains all the nodes in a particular expression. As you can see in this interface, it has a couple of interesting things. It's constructors and destructor, copy constructor, and assignment operator all use reference counting, which can be based again on C++11 shared pointers. We also have several operations that will forward to the underlying hierarchy, the composite hierarchy. For example, the item method, left, right, and most importantly, the accept hook method, which we'll see later when we talk about iterator and visitor. We also have an iterator trait, which is a feature, it's a pattern in C++ which we use to associate certain dependencies that the expression tree class has on things it depends on for use in algorithms and containers, things like iterators. And then we also have a set of factory methods that are used to create the appropriate types of iterators, both const and non-const iterators, to iterate through the tree. From a commonality point of view, we have a single common interface that are used for all the different ways in which we're going to access the nodes in an expression tree. From a variability point of view, we hide the different kinds of expressions, the different hierarchies of our component nodes behind a common interface. So we get both commonality and standard stable variability within the same class package. It turns out that this particular way of arranging the software is given a name. It's called the bridge pattern, which is a gang of 4 object structural pattern. The main intent of this pattern is to separate interface from implementations so that the interface and the implementations can vary in different ways without breaking client code. We keep the interface stable so clients can depend on it. It's closed with respect to usability, but we can modify and extend and enhance the implementation so the implementation remains open. The bottom of this slide illustrates the structure of this pattern. You have something called an abstraction, which in our case would be our expression tree class. And then that contains some kind of pointer or reference to the root of a hierarchy that's called the implementer hierarchy. In our case, that would be the component node would be the root of that hierarchy. And then we would have different kinds of concrete implementations, composite unary node, composite binary node, composite add node, and so on, that would inherit. And when a client makes an invocation on an operation through the abstraction, through the interface, that method forwards down through the implementer hierarchy to invoke the appropriate dynamically bound implementation from a subclass. Here's a very simple example of how you might implement a portion of this pattern in C++. As you can see, we separate the expression tree interface from the composite node implementations. We'll end up using the C++11 or boost shared pointer. So we have the root node being a shared pointer, which is a shared pointer of a component node. So it has a pointer to a component node. And then when someone passes us a component node pointer in our constructor, we turn around and let the shared pointer manage the life cycle of this pointer parameter. And the various constructors and destructors and assignment operators and so on manage that reference counting process appropriately. When someone invokes the accept method through the expression tree interface, which is the non-virtual one, as you can see here, it turns around and forwards it through this shared pointer down to the appropriate accept method that comes from the corresponding node in the composite component node hierarchy. and that part is dynamically bound. Take a look at this link at the bottom for more information about shared pointers and weak pointers in C++ 11 and Boost. Here's an illustration of how you can actually put this all together. We could go ahead and create our richly recursive composite component node structure, as we had shown in some of the earlier slides. And when we finally have that thing finished, we can then go ahead and take the pointer to that rich composite structure, hand it off to the expression tree, which is the interface for the abstraction part of the bridge pattern. And at that point onwards, everything else we do will be managed through that well-described, well-defined, and reference-counted interface object. The consequences of this pattern, there's a number of benefits. The implementation and the implementer hierarchy are decoupled. They don't have to have the same method names. You can have much more effective ways of changing and enhancing and extending the implementer hierarchy without breaking clients that depend on the abstraction portion of the interface. We can also have efficient use of value-based STL algorithms and containers that expect to have value semantics, and we can do this with reference counting so that the costs are kept to a minimum when we do the copying. The downside, of course, is we end up with a one-size-fits-all abstraction and implementer relationship, and not everything will work through that particular one-size-fits-all interface, although it works well for the kinds of things we're doing here. Some implementation concerns, some things to consider. How do you do the reference counting? How do you share implementers? We're using C++ 11 and Boost shared pointers. How do you create the right implementation? We'll see later on we're going to use various kinds of factory patterns to do that. And it's also worth noting that the bridge pattern is not as widely used in Java as it is in C++. In C++, it's often used to manage reference counting and memory management automatically. In Java, that's less of an issue, so the bridge pattern only gets used in a couple of circumstances. Speaking of which, there's some known uses. In Java, the Java socket class has a way of being able to plug in a socket implementer or socket object. And that can then be used as the implementer hierarchy to actually do the appropriate type of communication that the socket bridge abstraction or interface shields from clients. So you can change the behavior of sockets without changing the way its interface is used. The ACE reactor framework makes use of the bridge pattern to keep the reactor implementation fixed while varying the types of reactors, whether they be select reactors or wait for multiple object reactors and so on. And there are other various uses you'll find in windowing systems and other types of systems that are based on C++. So to summarize this particular section, the composite is used to define the internal data structure for our expression tree, and then we use the bridge pattern to simplify access to this data structure in our C++ code. You can also think about bridge and composite being used together in what's called a pattern compound. So that's not an uncommon way of being able to do things. You can build a composite and then hide the details of the composite structure and the way in which memory is managed by combining it with the bridge pattern.